here, but down here it's a little bit to the right of M. So somehow or other, as we're walking along M, we're seeing that line to the left of us, but then when we cross the point at infinity, we're now seeing that same line to the right of us. So somehow when you cross points at infinity, it does reverse orientation in a weird way when we interpret what we're seeing from this ordinary R2. So I hope that's not too confusing. Maybe the simplest way to really state it is that you can just imagine shooting a laser from this center point. It goes up, 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 but it connects, it's really a line that it's traveling along. It's going to go through that point at infinity. It's going to come up from down here and come back to where it started. So these two regions are connected. These two are connected. And overall, there are just two regions that the plane is divided into. Excuse me. A slightly more difficult question is if we have this above this configuration of three lines. So weirdly enough, in projective geometry, this is a triangle. And the reason it's a triangle is because these two vertical lines are vertical, and particularly they're parallel to each other. So they're going to meet at a point at infinity. So really, this is a configuration of three lines and 3 points in the extended plane. That third point is the point at infinity up there where these two vertical lines meet. So we really do have a triangle. It's just that one of its vertices is sitting at infinity. So if this triangle is going to divide the plane into regions, and the question is, how many regions does it connect it into? And if we color those regions, which coloring represents the configuration that we get? So does anyone want to try and answer that? Maybe initially, anyone else besides Manmohan, anyone else want to take, or anyone else who hasn't spoken, want to just take a guess at which of these is correct? In other words, this configuration of lines, this triangle, what regions does it divide the extended plane into? Anyone want to take a guess?
D.
Say that again. D. Okay. That's a good guess. And tell me why you're saying so. In particular, in D, we're seeing that the top left and the bottom are connected.
Wait. The two triangles are meeting at infinity, so they are different. So D cannot be the answer.
Yes.
Both the triangles are different. So let me just check. C.
Correct.
Because triangles are different, so yellow will. C is the option.
C. So yeah. So if we look at C, actually, it's not quite correct. You had the right reasoning when you said D in terms of the upper left and lower right being connected, and you're correct
sorry.
You had the right intuition about the middle two.
So I think second is the correct then.
Yes, exactly. So combine those two intuitions and you get B.
So maybe
can you now explain why B is the correct answer?
Okay, so first of all, because the two lines they meet at infinity, so these two triangles are different. So D is eliminated that way.
Which two triangles?
On the upper half and lower half, these two triangles are different.
So you mean this red triangle here?
Red and green are distinct. So D is eliminated naturally, and we can cross the region. If you see the B option in the top rightmost corner, if we trace a path, we can come back in the lower leftmost path. So that way these regions are connected.
You can draw a line like that. And the thing to notice about that, the reason that for example, you might think, oh, you can also draw a line here, a vertical line center.
But I would cross the yes. So that's it.
That vertical line will also cross the point where these other two vertical lines at infinity. So it'll actually go from one region to another. So that's why that vertical line does not connect this region and this region. But this line that we could draw, for example, if you can see my cursor, this diagonal line will connect this upper right yellow region to this lower left yellow region. So those are the same region. So that's correct. So so great. So now I think that we've done those. Let's now go back and let's address the question that was originally asked by Manmohan in exercise 2. So let me just pull up exercise 2, 1 second.
In this one which is in the screen. This one, sir. Why option C is not correct? From the left.
Sorry, it's hard for me to hear you actually. It's breaking up. Can you say that again?
I have to ask some question in this picture, the one on the screen.
The one under C.
The one on the screen, sir, the current screen.
Sorry, can you type in what you're saying? It's the audio quality is not very good, so I'm having trouble understanding.
Am I
Yes,
audible now?
No, not quite. It's breaking up quite a bit, so it's hard for me to hear exactly what you're saying. If you can type it in, that'll be great, actually, in the chat. Meanwhile, I'll just pull up the exercises. Okay, so you said option C, can we draw horizontal lines which connect regions? That's a very good question. Okay, so in option C, remember, which is not quite correct, you might be tempted to draw a horizontal line right here to connect the top left region to the top right region. Unfortunately, that will not connect these two regions as we might hope. The reason is that that horizontal line is parallel to this other horizontal line that's already there. So it's going to meet that bottom horizontal line at a point in infinity. So actually, it's going to be crossing from one region to another through that point at infinity. So these are actually disconnected regions. So I hope, okay, great. Okay, now what I'll do is I'll just pull up exercise 2, assignment 2. I don't know why this is not, sorry, I'm just trying, okay, stop share. And now I'll do a screen share here. So here's assignment 2. And we're looking at which number was this? Just remind me, that was which we were looking at. Okay.
Six number.
Number 6. Yes. How many pieces do 4 lines in P2 divide P2 into when no 3 lines are concurrent? Okay. So so I think, yeah, anyway, you all saw that what the answer is now, but we really need to draw a picture to do this properly. But the exact reasoning we were just using is all we need to solve this problem. So so maybe, yeah, unfortunately, I don't have a great way of drawing on screen right now. So let me, okay, maybe what I'll do is I'll leave it there because I think this gives you what you need to know. And now you also know the answer to expect. So see if you can draw a picture that makes that true. So the point is you want to draw 4 lines which are in an arbitrary configuration. So in fact, so one very confusing thing about this problem, I feel, is that you might think that the positions of the lines matter. So rather than tell you one way or another, I think it's a good problem to explore on your own, but try different configurations of the 4 lines. For instance, maybe you can try 4 lines where 2 are parallel here and 2 are parallel here. That's one way of drawing 4 lines. But you could also try drawing 4 lines, none of which are parallel. And you can see for yourself how the answer changes, if at all, in those 2 scenarios. Or you could draw 4 lines where 2 are parallel, but the other 2 are not parallel. And using this kind of reasoning set of maybe draw those in one color with a pen, and then with a pencil, just on your piece of paper, see which regions are connected to each other, and see in the end how many different regions you get. The answer is going to be 7, but I think it's a very useful and kind of exercise to explore on your own, and to also convince yourself how the configuration of these lines matters or doesn't matter. So I hope that's helpful. If anybody has a question still, please ask, because I want to make sure you can do this on your own. Okay, so Manmohan's asking, it'll depend on the configuration. If all 4 are parallel, then there are only 4 different regions. Are you missing something? Very good question. Let me draw a quick picture for you. 1 second. So All right, so the question is like, if we draw all four, you're saying if all four are parallel. Okay, so if it's 1, 2, 3, 4, then, yeah, so you're actually talking about this bottom configuration. Then there are only 4 different regions. And let me give a boundary here. It's easier to see. Yes, and you're absolutely correct. In this example, you're not missing anything. There are exactly 4 regions in this case that are disconnected from each other. There's these 3 middle regions, and then this outer region, which is connected to this outer region here. So there are 4. So indeed, the configuration does matter a little bit. And yeah, and for that reason, I'm actually but now we have an additional assumption here. We have 4 lines, no 3 lines are concurrent. So that additional assumption is going to matter a lot. If we have, I should have been a little more clear when I was reading the question. So that's my fault. If we, yeah, the configuration very much does matter if we have 4, because we can do something like this and make our 4 lines parallel. However, if we have the additional condition that no 3 lines are concurrent, then we still have a lot of freedom, flexibility in how we draw these 4 lines. For example, this configuration I drew here, no 3 lines are concurrent. It's true that these 2 lines, I mean, any 2 lines are going to be concurrent. So these 2 lines happen to have they meet at infinity, these 2 lines meet at infinity, and you could have them meet at ordinary points and not be parallel. So what I meant to say really or suggest is that doesn't matter. It doesn't matter whether points meet in the ordinary plane or at infinity. That's not going to change your number of regions. But you do need this condition that no 3 lines are concurrent. So I hope, does that clarify the question, Mohan, and to other people? Okay. Yeah. So we do consider those as being concurrent. Yeah, by the way, for those of you who have maybe seen some of these terms before, there's another, you might say that these lines, when no 3 lines are concurrent, another way of saying that is that these lines are in general position. That's another mathematical term. If you've heard it before, I thought I'll throw it out since that might connect to other things you've studied. If you haven't heard it before, don't worry about it. It's just another term, which basically says that they're not in a very specialized position. If you were to randomly plop these lines down on the projective plane, then that's the kind of case we're interested in. To have 3 lines be concurrent, that's very specialized. So we'd have to put some effort or work into making sure our lines have that property, that constraint. So we're really looking at the more general configuration of 4 lines in the projective plane here. So as an exercise, yeah, I guess I've essentially told you this at this point, but yeah, it doesn't actually matter whether you take this case or if you take a slightly less specialized case like this one here. Really, from the projective geometry point of view, these are the same. This one where they're parallel in the ordinary plane, where their intersections are at infinity, and this one here, where their intersections are actually happening in the ordinary plane if we just keep extending those lines outward. Those scenarios are really the same for a projective geometer, and we're going to get the same number of regions in either case. So you can use either one in your investigation. So Ritabrata, when you say last case, what do you mean actually? When you say it's dividing the plane into 5, do you mean this? You can turn on your mic if you want. Are you talking about what I drew here?
No, sir, the one that's above. Oh, wait.
Okay. You want to know about this? Okay,
Yeah,
so
that's one.
yeah, so let me get a different color. 1 second. Okay. So here, okay, I have another color now. So this is my main configuration, okay? And let's say we want to just imagine a line going through, imagine this horizontal line here. You might want to say that this connects this region here and this region here, but it doesn't for the same reason that we saw earlier in the previous problem, which is that it's actually horizontal. So it's parallel to this and this. So it's actually going to go through the point at infinity, the upper vertex, the vertex of the triangle that these two lines make. So these two regions are going to be distinct. And I don't know if that helps at all.
Oh, yeah. I missed that one. Sorry.
Okay, no problem. Yeah, so yeah, see if you can convince yourself though that there are in fact 7 regions. So yeah, any other questions about that problem? Or if we can also, any other questions about that problem first? Yeah, I know a couple of people also just came in, G3 and Kavya. So if you have questions, please feel free to ask. You can either use audio or you can type in your question into the chat. We were just looking at a question from week 2. All right, so I know the first question that Manmohan asked was from week 1. So let me take a quick look at that. So his question was about assignment 1, about the final question on assignment 1, which was that if we have an artist standing let me share screen. Okay, so hopefully you can all see this question, number 20. So it says that an artist stands exactly on top of the intersection of a pair of perpendicular horizontal lines. So in this picture here, we're seeing a bird's eye view. So there's these perpendicular blue lines, and the artist is standing at the intersection of them. So the feet of the artist are on these lines, and her head is directly above the intersection, you can imagine. Actually, it doesn't matter where her feet are. The important thing is that her head is above the intersection. So the artist sets up a large vertical glass plane in front of her on this diagonal, which is crossing both lines. And the question is, if the artist just draws on the glass plane exactly what they see, what image will they end up drawing on the plane? So her head is fixed at this point of intersection, but she can turn her head as she's drawing. In fact, you can imagine her looking. Again, that doesn't really matter. She could be looking this way, she could be looking this way, she could be looking this way. That's actually not going to affect the drawing that she makes, because this is a bit of an approximation. This is like when, physicists say, consider a spherical cow. We're basically saying that let's just imagine that she has one eye. So and that her eye is fixed at this center point. That's kind of the idealized version of this thought experiment. So her eye is fixed at that center point, and what she draws on the glass plane is exactly what she sees. So as she sees if she's viewing these blue lines on the ground plane, she's just going to draw them exactly as she sees them. So as she follows these blue lines out further and further and further with her sight lines, the places where those sight lines intersect the glass plane, those are going to be the points that she marks on the glass plane. So, okay, so coming back to the question, what image will be drawn by her? So again, unfortunately, this PDF has the answer, but can anyone explain the answer to me? Can anybody tell me what the answer is and why that's the answer? Yeah, Manmohan, or any of you. Manmohan, is it, maybe first I'll ask you since you asked the question, are you having a better sense of the answer now, or is it still confusing? And it's fine if it's still a bit confusing, because it is a very counterintuitive question, and it's not a very realistic one. We wouldn't encounter this very easily in real life. Yeah, or anybody else if you want to pipe in. Yeah.
I also haven't understood.
Okay, Okay, cool. Okay, so let me just go back to the picture. So basically, the reason that we're getting A as our answer, the reason that from her point of view, you're going to get two lines that appear parallel in the picture plane is because from the sight lines, as she looks further and further and further along, let's take from this bird's eye view, let's look at this line first, this one that appears vertical in the bird's eye view, okay? And let's just imagine what the drawing of that would look like in this picture plane. Well, as she looks further and further and further down along this line, what's happening to her sight lines? And what's happening to their intersections with the glass plane? Well, weirdly enough, as she goes further and further along, as she looks further and further down this blue line, her sight lines are going to be going higher and higher up. But they're going to be going vertically up. And the reason for that is that she's standing on this line. So her sight lines, as she's looking further and further down the line, are always going to be in the vertical plane that intersects this blue line. All of her sight lines are trapped in a vertical plane that intersects this blue line because she's standing on this blue line. So in particular, another way of saying that is whenever you try and draw a picture on a glass plane of a line that you are standing on, that line is going to appear vertical in your picture plane. Because as you look further and further down it and keep marking the points that your sight line pierces the plane on, those points are just going to be moving. Those points are just going to be moving higher and higher up. So imagine that I'm here standing on the ground, I'm standing on a line, there's this picture plane in front of me, and I'm just drawing the line that I'm standing on. But as I look further and further down, my line is just moving up vertically, moving up till it reaches my height, the height of my eye. And I'm just going to get a vertical line segment that goes from the ground up and terminates at the height of my eye. So that's what I'm going to get for any line that I'm standing on. So in particular, she's going to get it for that one line that she's standing on. And then for the other line she's standing on, she's going to get the same thing, another vertical line segment that starts at the ground and terminates at her eye level. So I don't know if this is helping at all, but please let me know. Can one of you who just spoke is any clearer?
So, for example, rather than this orthogonal coordinate system, if we had the angle between x and y axis, suppose 45 degrees or 60 degrees in the first quadrant, then the answer would still be the same.
Correct. That's correct. That's correct.
That
It's
is,
not the fact that it's a right angle is a red herring. That doesn't change it.
It is very, very counterintuitive. P2 is very difficult.
Yes. Yes, it is, but somehow at the same time, it's very, we end up using it all the time for photographs and for perspective drawings. And so we end up, it's intuitive unless we go to some extreme examples where things really become weird. But for the most part, yeah, it's both intuitive and counterintuitive, I guess. So, yeah, any other questions, or is it still unclear? Maybe Mohan, is this any clearer to you? And that's a very good point that Pratik made. That right angle that these two blue lines are intersecting at, that's actually misleading. It doesn't matter that they're right angle. They could have been 60 degrees or 30 degrees apart. The picture would have still been very similar. She would end up drawing. Okay, so maybe let's move on. Okay. What do we mean by perpendicular and horizontal lines? Okay. So let me just go back to that picture. And this picture here. So what I guess the perpendicular that I'm referring to now is that the blue lines here are perpendicular. And the yeah, so that's a bit confusing. I agree. So in real life, this artist is standing somewhere in real life. By horizontal, I mean, really what I should have said here is that they're horizontal in the sense that they're on the ground. She is standing on a flat plane, on a flat ground, which is horizontal. And these lines are also on the ground, so they're also horizontal from her point of view in that sense. They're parallel to the ground, and they're perpendicular to each other. Though, as Sandeep just said, that part is a bit of a red herring. That's not significant. They could have been intersecting at a different angle, and that wouldn't change the answer. So she's standing in a room, say an infinitely large room, on a flat ground. These blue lines are horizontal in the sense that they are on the ground. And okay, let's just, to keep it straightforward, they are perpendicular to each other. So she's standing at the point of intersection of these blue lines. Okay, so I think maybe we'll move on now. The Devkar is asking, there was a problem where we had to find viewpoint of observer on the picture plane where 4 points A, B, C, D were given. Okay, yes. Let me just find that. So yeah, do you remember where that question was? I'm just trying to find it right now.
That was in the third lecture.
That was in, yeah, the 3C, I guess.
3C. Okay. Wait, sorry. This is not the question you're asking, right? The eye level relative to.
Yes, this is not the one.
Okay. Okay. I think yeah, so okay, I remember the question you're asking. Sorry, that's in which, where was that question though? Where we're trying to find the viewpoint of the observer, where 4 points A, B, C are given. This should be in a second.
Sir, it was about, first of all, we have considered that some tiling which is in 2-point perspective, it is square. Then we have to find the viewpoint.
Does anyone remember which lecture it's in?
Sir, it's in third lecture.
The third lecture. Okay. So I thought at first. So where did it go? I see. It was I see. It was only in the video. It wasn't outside of the
It
video.
was in the video. It was not out in the
Correct.
YouTube.
Yes. I thought I had done it outside of the video also, but I forgot I didn't end up doing that. Okay. So this is a very good question. This one is a bit tricky. But it involves basically, okay, so first I'll answer Manmohan's question about it. The same problem, so 2-point perspective of a square. What exactly does that mean? So what that means is if you see this picture here, we can assume, so a priori, if we just see this picture and we don't have any additional information, what do we know about this? All we know is that this is a perspective drawing that somebody has made of something they see in front of them. In that situation, with no additional information, this is clearly, we do know that this thing that they've drawn, this object that they've drawn is a quadrilateral. We don't necessarily, we also might suspect that it's not just a quadrilateral, but a rectangle because, or rather a parallelogram, because these two opposite edges, oops, sorry. Oh no, 1 second. These two opposite edges intersect at a point at infinity. These two opposite edges intersect at a point at infinity. We have a horizon line. So it's reasonable to think, okay, this is an image of a parallelogram. But now I'm giving you some additional information. I'm saying this is not just the image of a parallelogram. This is the image of a square. So this person, this artist, they saw a square, actual honest square tile sitting in front of them, and they drew a perspective drawing of that. So in real life, this tile that they've depicted here is actually a square. That's what I mean in answer to Manmohan's question by the phrase 2-point perspective of a square. And we need to use that to do this problem. We need to use the fact that this is actually a square. So, second, I think there's another image here. Let me just see. Yeah. So now you see here that this is the top-down view of the artist drawing this tile. And from the top-down bird's eye view, it's actually a square. We see that here. So using that fact that it's a square, the question is, can we figure out the viewpoint of the observer in the picture plane, where their eye is? So so in particular, we have that this is a right angle. And since, sorry, let me get that up again. So we know that since it's a square, this angle is a right angle. So what that tells us is that if we imagine drawing these two sides of the square, the viewer's sight line will keep going and going and going along this line in space till it gets to this limiting sight line, which intersects the picture plane at point D. So this line of the square is going to converge to the point D on the picture plane, and this edge of the square, its image in the picture plane is going to eventually converge to the line B, if you were to follow it along beyond the square and just follow it on infinitely long, infinitely far. So in your depiction, going back to, but in particular, wherever this viewer is, that means that, so this line from the origin, from the viewer's eye to D, is also going to be perpendicular to the line from the viewer's eye to B. This line and this line are going to be perpendicular because these two lines were perpendicular. So going back to the original picture, where was that? Here, B and D, we know their locations, but now we know that wherever the viewer is, wherever the viewer's eye is, it has to meet point B and point D. If you draw the lines connecting it to point B and point D, we need to get a right angle here. So now we can kind of figure out where the viewer is sitting by that fact. Wherever the viewer is sitting, there's many possible places, but we know that the angle that the viewer's eye makes when we connect it to B and we connect it to D, in other words, when we draw the point B, O, D, we need to get a right angle. So this is where this reasoning. So once we know that, we can apply a very classical result from geometry, which you must have seen at some point, though you may have forgotten about it, but it's a very useful result. So namely, the result concerns the set of given 2 points, like B and D. Suppose we want to look at all the points O such that BOD forms a right angle. So my question is, what will that set of points look like? So can anyone tell me that?
A circle?
A circle, exactly. This is Thales' theorem. So if we fix points B and D in the plane, and we look at all of the points O, which such that BOD forms a right angle, that set of points, that locus, is going to be a circle. And so in other words, and in particular, it's going to be a circle that passes through B and D. And it's going to be a circle for which BD is the diagonal, or the, what do you call it? The diameter of the circle. And so we're going to get a circle that looks something like that. So O is sitting somewhere on that circle. So already we have a much better sense of where the viewer's eye can be. It has to be somewhere on this circle connecting B and D. But now we're not finished locating the viewer's viewpoint, because we still haven't used all the information. We've used that this is a rectangle, that this is a right angle, but we haven't used that it's a square. So we have some additional information that we can use. So what's a special feature of a square? That all rectangles have the feature that their corners are right angles. If you want to make sure your rectangle is actually a square, what's an additional constraint you can put? Is there any easy way to check? What are some ways to check that a rectangle is a square? Are there any other places that right angles, can you characterize a square purely in terms of right angles? I guess that's a better way to ask my question.
Diagonal intersection.
Exactly. The diagonal intersection of, if the rectangle is a square, then the diagonals are going to intersect at a right angle. If the rectangle is not a square, imagine a long rectangle like that, then the diagonals are not going to intersect at a right angle. So that's an easy way to characterize squares purely based on right angles. So to finish this problem, to really find exactly where the viewer's eye is, we need to use that second property, that the diagonals intersect in a right angle. Since the diagonals intersect in a right angle, we can follow the diagonal lines with the viewer's eye to points A and C. Going back to this picture. Points A and C. That's where the diagonals are on the horizon line. Diagonal lines converge on the horizon line. We know that wherever the viewer is, if we draw points A and C on the horizon line, the viewer's eye will also connect to A and C at a right angle. So the viewer's eye will also have to be on a circle, a semicircle that goes from A to C. So now we know that the viewer's eye is both on a semicircle connecting, actually, sorry, let me go back to this picture. It's both on this semicircle connecting B and D, but it's also on the semicircle connecting A and C. So it's in the intersection of those two semicircles. And that completely determines where the viewer's eye is. And in particular, it completely determines the viewer's viewing position. So we have to use Thales' theorem twice to do this. So this was definitely a harder problem. It was kind of a challenge problem, but I hope that makes some sense. And I'm realizing I really should have plugged in my iPad so I can do some drawings properly. So sorry about that. But is this a little bit clearer, or are there any more? Would anyone like some more clarification on that?
So instead of that joining A and C, can we just extend the diagonal and basically make the semicircle that is, and from there we can draw the perpendicular?
No, that's a good question. Let me just show the picture again. I think what you're asking is, can you extend these two diagonals from the top-down view and see where they intersect the picture plane? Like extend this diagonal down to here and extend this diagonal over somewhere here, correct? Is that what you're asking?
No. I mean, we can extend one diagonal and check where this diagonal meets the semicircle that circle by B and D.
So we have a semicircle from B and D, and which diagonal? Maybe let me. So are you saying like extend this diagonal here, for example? Is that
yes,
what you're saying?
Yes.
Okay. So you're saying extend this diagonal down, and see where it meets this semicircle that connects B and D.
Yes. And from there we will draw a perpendicular.
And from there, what?
From there we will draw a perpendicular to that original line. That will be the viewpoint.
From there, draw a perpendicular to the picture plane. Is that what you're saying?
Yes, sir.
I don't think that'll work because I don't see why that would work. Can you explain your reasoning? Because yeah, I don't see any reason why that should work, because that diagonal where it intersects, I mean, yeah, so this picture is actually kind of useful because we have A, B, C, and D all marked. So you can imagine drawing a semicircle connecting B and D. You could imagine a semicircle connecting A and C. And yeah, in some sense, we need to know where those two semicircles intersect to really narrow down where our viewpoint is on the left-right axis. So yeah, so I don't see how following this diagonal to where it intersects the semicircle and then drawing a perpendicular up. Yeah, I'm having trouble interpreting what that would even represent. But maybe if you have some other, maybe you could, if I'm missing something that you're saying, please clarify.
There actually C is lying between B and D. So if
Correct.
we're drawing a semicircle from AC and BD, then there will be some curved path in which between B and C we are getting a point. Okay.
Correct.
If we are taking a straight line, that is, it is also joining C basically, the diagonal. So it will not follow a curved path. So it will take some other point. So
Yes.
the answer will be different.
Yes, exactly. So that won't give that won't give the correct answer. That's right. That's right. Yeah.
Sir, actually, I have thought a reasoning, but currently I missed that. I mean, during that, during when I watched the video, I have thought this reason, but right now I'm not able to recall that. Maybe I can later on think about.
We can. Okay, feel free to get in touch later. We can talk more about it then. We can. I mean, if you want to write it to me on the forum or in an email, I'll get back to you.
Okay.
Yeah. Okay. Cool. So I think we have time for one more question or one more topic if anybody wants to ask about anything else. So let's move on and try and cover one more thing. And again, it can be a specific question, or it can also be a topic that you want to know more about or that you didn't understand. So does anybody have an additional question they'd like to go over?
Assignment 2, can we just discuss question number 4?
Yes. So assignment 2, I'll pull it up quickly. So question number 4 is asking which of the following depicts, one second. This is the question about the restriction of a triangle in P2 with exactly one ordinary point, correct?
Correct, yes.
Okay. So Okay, so here, so which of the following depicts the restriction of to R2 of a triangle in P2 with exactly one ordinary point as a vertex? So as you can see, the correct answer is A. So first of all, if it has exactly one ordinary point as a vertex, so first of all, let's look at the other examples and see why they don't work. So example B is indeed a triangle, but it has two ordinary points.
Correct.
So that won't work, but it is a
Yes.
triangle. Part C, that is also a triangle, but how many ordinary points does this have? I haven't drawn them all, but actually how many ordinary points does it have?
All three ordinary.
3. It has 3 ordinary points, because if you continue these lines further, they intersect at another ordinary point here. So part C is again a triangle in P2, but it has 3 ordinary points as vertices. Part D, answer D, this indeed has just one ordinary point. We're looking at 3 concurrent lines here. But is this a triangle? And I suppose maybe here it's useful to have a better definition of what a triangle is. So, so when we talk about a triangle, we really mean a configuration of three lines that are not concurrent. This will not be a triangle, and in fact, it's and whatever it is going to, and this is also going to divide the plane into how many regions, going by our reasoning from before. In part D, this configuration of lines, how many regions will it divide the plane into? Notice that none of these lines are parallel to each other. So this configuration involves no points at infinity. No, there's no intersections at infinity that are happening. So like this top region here will in fact connect to this bottom region here. This region here, this northeast region here, will indeed connect to this southwest region here. This northwest region here will indeed connect with this southeast region here. So we've got 3 regions. So it's behaving very differently from a triangle. These lines are concurrent. So this is not actually a triangle. So part D fails because it's not a triangle. Part C is a triangle.
Actually, option D was very, very confusing.
Yes, option D is very, very confusing. It's not at all a triangle, basically. So it's just there to be confusing, basically. But it shows, yeah, but it's something that can happen when you have 3 lines that are, it's also a common configuration because it's just what we get when we have 3 concurrent lines, 3 lines that share a point. So, so that leaves option A, and option A, notice, is this a triangle? That's a bit harder, maybe that's a bit harder to see. Because we're not seeing 3 lines, we're only seeing 2 lines here. But remember, we're looking at the restriction of a triangle in P2 into the ordinary plane R2. So how can we think of this as a triangle? This option A.
So maybe we can join the line at infinity.
Yes, if we include the line at infinity as our 3rd line, then this is indeed a triangle, because we'll have 3 lines, we'll also have 3 vertices. This line, vertical line, will intersect the line at infinity at one point at infinity. This horizontal line will intersect that same line at infinity at a different point at infinity. So this triangle will consist of 1 ordinary point and 2 points at infinity. And it'll also consist of 3 lines, these 2 ordinary lines and that 1 line at infinity. So this is also a triangle, and it satisfies these conditions. It has 1 ordinary point as a vertex and 2 points at infinity as vertices. So yeah.
Can we count the number of regions in option A?
Yes, that's a very good idea. So let me share screen again. Yes, so in option A, let's try and count the number of regions. So first of all, remember we do have the line at infinity dividing up regions now, because the line at infinity is one of the sides of this triangle, one of the lines of this triangle. So how many regions are there? Let's try and figure that out. Does anybody have a guess, or can anybody explain to me how many regions there are and how we might?
I guess there are 4 regions here also.
Yes, exactly. And the reason is because that line at infinity is dividing up regions as well. That's also included in our set of dividing lines. So that trick we were doing earlier of looking at a line and seeing which regions it connects, well, any line as it passes through infinity is going to pass through the line at infinity. So it's always going to go from one region to another when it passes through infinity. So now all these 4 regions are distinct. This region is no longer connected to this region because they're separated by that line at infinity. This region here is no longer connected to this region here because it's separated by that line, and they're separated by that line at infinity. So all 4 of these quadrants are separate regions now. So in fact, it's just like the triangles that we were looking at. So part B is also a triangle. We already considered that case, and we saw that that divides the plane into 4 regions, right? One is this one here, 2 is this other diagonal region here, 3 up here, and 4 down here. So we had 4 regions there. Again, we have 4 regions here. And in part C, you can check for yourself that once again, we should have 4 regions. So any triangle will divide the plane into 4 distinct regions. And it's a nice exercise to check for yourself why part C divides the plane into 4 regions exactly. So does that make more sense, Devkar?
Yes, sir.
Okay, cool. And yeah, I would recommend as an exercise, just try for yourself with this triangle in part C, where we have all 3 vertices are ordinary points. Check for yourself how many regions that divides the plane into. We have our central, unfortunately, to make the problem trickier, I didn't complete the drawing, but imagine this line and this line are extended. Even this line, imagine it's extended. It helps to draw it on paper. So really what I'm asking you to do is something like this, and check that this really divides the plane into 4 regions. We clearly have our central region, but then we actually look like we have 1, 2, 3, 4, 5, 6 other regions, but you can check which of those regions are actually the same, which of those regions are connected. And hopefully you'll get in the end that we have a total of 4 regions. Okay. Now, yeah, I guess officially the office hours are over, but I don't mind staying a little longer if there's other questions. So if we have any more questions, I'm happy to talk about them. Okay. Yeah, okay. Yeah, Pratik, you tell me your question first.
Just the last, for the second assignment, question number 12.
Okay, second assignment, question number 12. So we're okay, so here we're looking at the harmonic conjugate of okay, yeah, so let me just pull that up. You're looking at number 12, which is asking for the harmonic conjugate HAC of A.
Yes.
Yes. And yeah, basically the construction we used to construct the harmonic conjugate, to draw the harmonic conjugate, that kind of doesn't really make sense when we take HAC of A, because we can't draw all the lines that we need to and have the intersections that we want. Yes. So that's why we use this limiting construction. We take HAC of X as X approaches A. And it can approach A really in any way we want. So because we have complete freedom sorry. I mean to say, sorry. We can approach, from either side, basically. We can approach A from either side. And then we can determine what HAC of A is. So, so let me just pull up a picture of that. 1 second. Okay, so let me do a screen share. Okay. Okay, so basically the construction for the harmonic conjugate is to choose a P that's not on L. So if we're looking at HAC of B, we choose a P that's not on our horizon line. We choose a Q on that line connecting it to B. We connect C to both of those points P and Q. We connect A to those points P and Q to get this quadrilateral, PRQS, to get that quadrilateral. We take the other diagonal of that quadrilateral, and that gives us our point D. So obviously, if we take our point B to just be equal to A, this construction is going to be difficult to do because at this stage, when we connect C and A to P and Q, well, we're not going to end up getting a quadrilateral in the way that we want. So instead, we have to just make B go closer and closer to A. And again, here, the best way to do this is to draw a picture. But if you draw a picture where B is very close to A, let me see if I have a picture here later on. 1 second. Sorry. Yes, so if you look at this picture here, where B is closer to A, what's happening to D? It's also going closer to A.
Yes.
And eventually, as B reaches A, D will you can draw an example. Unfortunately, I didn't do it here, where B is really close to A. D will also get really, really close to A. So basically, yes.
I actually missed the significance of that limit defined in the question. That's why.
I see. Okay, but really, that's all the question is asking. It's just
Yes.
that as B gets closer and closer to A, D will also get closer and closer to A, because that quadrilateral we're drawing is becoming narrow, and its diagonal is basically approaching, that other diagonal is basically approaching the line from A.
Yes,
So,
it is clear now.
Okay.
Sir, if you can consider A and B are the same points, then this line A, P, and Q will be like these 3 points A, P, and Q will be equal.
Yes.
With this QP, this line will meet the line at the point A. With this also Q is.
Yes, I think so. I'm sorry, it's very difficult for me to hear what you're saying. I think something is with your audio is difficult to hear. So are you? Yeah.
I'm saying that if we consider the points A and B are same, and in that case, the 3 points P, Q, and A will be equal. And so this line joining P and Q will meet this first line at the point A itself.
Yes, that's another way to think about it. That's also a reasonable way to think about it. So that's right. Yeah, just that in that case, we don't really have a quadrilateral. So it's not quite the same construction, but that's a good way to think about it. So yeah, and it looks like you have one more question. In Desargues' theorem, can the center of perspectivity be interior to any one of the lines AA, BB, or CC? And the other question you have is that when can the center of perspectivity be interior to? I see. Yeah. Yes, that's a very good question. So yes, the center of perspectivity can actually be anywhere and the theorem will still hold. But to interpret it as a light source, physical interpretation becomes very funny if we put the center of perspectivity in the interior, for example. So, so yes, the math works out, in the theory works out, the theorem is still true, but our physical interpretation breaks down. So unfortunately, that's the case with a lot of these theorems in projective geometry. We have a nice physical interpretation for a certain subset of cases. But for the general case, our physical interpretation might break down. It no longer really makes sense. And that's exactly what's happening in the situation you just asked about. So yeah, I mean, I like the physical interpretation because it gives a more intuitive sense of what Desargues' theorem is saying. But eventually we also have to let go of that physical interpretation and step back to the more abstract interpretation to get the full impact of the theorem, to really understand everything it's saying. So in full generality. So I hope that helps. Yeah, any other final questions? Okay. Okay, so I guess if there's no more questions, then we can end here. Feel free to email me with questions or post questions on the forum. We are checking the forum, myself and the TA. So we'll be responding to questions in the forum. If you have, maybe I'll give you the forum link also. 1 second. Hopefully you have it already, but in case you don't, let me just give you that. So that's the link to the question forum. And you can also email me. My email address, I'm just writing here. You can use my Gmail address, that's fine. That's a guaranteed way to get in touch with me also. So yeah, so just either of those ways you can contact us for with more questions. And yeah, I guess that's it. So
is there
yes.
any such similar session planned again?
We can definitely do another session next week. So maybe on, let me think for a moment. So if right now there's no set date for it, but yeah, but we could do a session, say on
maybe when week 4 ends.
Maybe so when week 4 ends, we could do that. That actually works best, because yeah, I'm actually traveling right now, and next week is when I'm flying back to India. So for the end of the week would work best for me, actually, if that's not too late. So maybe just a little more than 1 week from now.
So by that time, hopefully I will understand P3 better.
Okay, yes. I mean, P3 is indeed difficult to understand, but the thing to keep in mind is that it's, yeah, I mean, the way we're thinking of it right now, it's really a generalization of P2, in that just like we built P2 by saying, okay, any 2 parallel lines in R2 share a point at infinity. Now in P3, we're saying the same thing. Any 2 parallel lines R3. So we're adding lots more points at infinity to R3 to build P3. And then we also have to add lines at infinity, which connect some of those points at infinity. And finally, we add a plane at infinity that includes all of those points at infinity. So it does take quite some getting used to. It's not easy. And especially dealing with questions of intersection and incidence in P3 does take a lot of getting used to. So, but there is a method to the madness. So
hopefully we'll get used to this.
Yeah, I hope so. And really feel free to message if you have any questions. So.
Sure. Thank you, Professor Vijay.
Okay. Yeah, thank you. Thank you all. So
yeah, thank you, sir.
Thank you. Thank you. And yeah, we'll do a session next week at the end of the week. And I'll send you an email about that sometime next.
Yeah, okay, sir.
Okay. Okay, great. Yeah. So take care and good luck with the rest of the class. Okay. Okay. Bye.
Thank you. Bye.